Imagine standing at the edge of the ultimate abyss, a black hole, where gravity is so powerful that not even light can escape. What would actually happen if you fell in? Would you be crushed instantly? Stretched like spaghetti? Frozen in time? The reality is stranger than any science fiction. Tonight, we'll take the ultimate journey, falling past the point of no return into a black hole. We'll experience the approach where strange relativistic effects begin warping space and time around you. We'll cross the event horizon, that mysterious boundary beyond which escape becomes impossible. We'll feel the tidal forces stretching your body in ways no human could survive. And we'll descend toward the singularity, where the known laws of physics break down completely. We'll explore the profound paradoxes, how you'd appear frozen in time to distant observers even as you experience falling through in finite time. How information might be destroyed, violating quantum mechanics. How rotating black holes might harbor wormholes to other universes. This is a journey into the most extreme environment in the universe, where reality itself becomes unrecognizable, and the final moments reveal the deepest mysteries of space-time. Before we can understand what happens when you fall into a black hole, we need to understand what black holes actually are. These objects represent the ultimate triumph of gravity over all other forces in nature. A black hole forms when matter becomes so dense that its gravitational field prevents anything, even light, from escaping. This typically happens when a massive star runs out of fuel and collapses under its own gravity. The outer layers might explode as a supernova, but the core continues collapsing, crushing matter to incredible densities. For stars with cores above about 3 times the Sun's mass, nothing can stop the collapse. The core crushes past the neutron star stage, where matter is already compressed to nuclear densities and continues shrinking. It collapses past any stable configuration, becoming smaller and smaller until it forms what we call a singularity. The singularity is a point of infinite density where all the black hole's mass is concentrated. Our current physics cannot describe what happens at the singularity itself. The equations of general relativity, which describe gravity, break down. The singularity represents a place where space-time curvature becomes infinite, where the known laws of physics fail. Surrounding the singularity is the event horizon, the defining feature of a black hole. The event horizon is not a physical surface. You couldn't touch it or bounce off it. Instead, it's an imaginary boundary in space, a point of no return. Once anything crosses the event horizon moving inward, it can never escape or send signals back out. The size of the event horizon depends on the black hole's mass. For a non-rotating black hole, the event horizon radius is called the Schwarzschild radius. A black hole with the Sun's mass would have an event horizon about 3 kilometers in radius, about 2 miles. A black hole with 10 times the Sun's mass would have an event horizon about 30 kilometers in radius. Supermassive black holes, the monsters lurking in galaxy centers, have event horizons millions or even billions of times larger. The supermassive black hole at the center of our Milky Way galaxy, called Sagittarius A star, has a mass about 4 million times the Sun's, and an event horizon roughly 12 million kilometers in radius, about 17 times the Sun's radius. The event horizon grows in direct proportion to mass. Double the mass, double the radius. This seems simple, but it has profound implications. The average density inside the event horizon total mass divided by the volume enclosed decreases as mass increases. A stellar mass black hole of 10 solar masses has incredibly high average density. But a supermassive black hole of 1 billion solar masses has average density lower than water, despite being a black hole. This doesn't mean supermassive black holes are somehow less dangerous. The average density is misleading because all the mass is actually concentrated at the singularity. The event horizon simply marks the radius at which escape becomes impossible for that given mass. Black holes come in several types based on their properties. The simplest is the Schwarzschild black hole non-rotating, with no electric charge, described completely by its mass alone. This is the easiest type to understand theoretically, though probably rare in nature since most stars rotate. More realistic are Kerr black holes, rotating black holes. When a massive star collapses, any rotation it had gets amplified enormously as the core shrinks, like an ice skater pulling in their arms. The resulting black hole spins rapidly. Rotation adds complexity because it drags spacetime around with it, creating effects not present in non-rotating black holes. There are also charged black holes in principle, though these are probably rare. Electric charge would be neutralized quickly by attracting opposite charges from the surroundings. Black holes are characterized by just a few properties: mass, spin, and charge. This remarkable simplicity is called the no-hair theorem in physics. It means that once matter falls into a black hole, almost all information about it is lost. You can't tell whether the black hole formed from hydrogen, iron, or antimatter. You can't tell if it formed from a star or from compressed radiation. Only mass, spin, and charge remain. Despite their name, black holes aren't actually holes. They're objects, incredibly compact objects with mass, gravity, and presence in space. The hole terminology comes from their appearance. Since light cannot escape from within the event horizon, the black hole appears as a perfectly black sphere against space. It's a region where light goes in but never comes out, creating an absolute darkness. Around the black hole, spacetime itself is warped. Mass curves spacetime. This is the fundamental insight of Einstein's general relativity. Earth curves spacetime slightly, creating what we experience as gravity. The sun curves it more. A black hole curves it to the extreme. Near the event horizon, spacetime is curved so severely that all paths lead inward. Even light, traveling in what it thinks is a straight line through curved spacetime, finds all its straight lines leading into the black hole. This spacetime curvature creates the black hole's gravity. Gravity isn't a force pulling you in the traditional sense. Instead, you're moving along the natural paths through curved spacetime. Near a black hole, those natural paths spiral inward, and beyond the event horizon, they all lead to the singularity. Black holes also have temperature and can radiate energy, though this is a quantum effect discovered by Stephen Hawking. Hawking radiation arises from quantum fluctuations near the event horizon. For stellar mass black holes, this radiation is incredibly faint, far cooler than the cosmic microwave background. The black hole absorbs more radiation from space than it emits. Only extremely tiny black holes, if they exist, would radiate significantly. Despite radiating energy, black holes can grow by accreting matter. Material falling toward a black hole usually has angular momentum. It's moving sideways as well as inward. This material can't fall straight in. Instead, it forms an accretion disk, spiraling gradually inward while heating to extreme temperatures from friction. The accretion disk can be incredibly hot and bright, radiating across the electromagnetic spectrum from radio waves to X-rays. This radiation comes from material outside the event horizon. We can observe accretion disks around black holes, seeing the light from doomed matter in its final moments before crossing the event horizon, but we never see light from inside the event horizon itself. Some accreting black holes produce jets, narrow beams of particles, and radiation shot out perpendicular to the accretion disk at nearly the speed of light. These jets can extend for thousands of light years. The mechanism involves the black hole's spin and magnetic fields in the accretion disk, extracting rotational energy and channeling it into the jets. Black holes are among the most extreme objects in the universe. They represent the endpoints of stellar evolution for the most massive stars. They power quasars and active galactic nuclei, the most luminous objects in the cosmos. They create gravitational waves when they merge, ripples in spacetime detected by instruments like LIGO, and they serve as natural laboratories for testing general relativity in its most extreme regime. Now, understanding what black holes are, we can begin our journey. What happens when you approach one? What do you experience as you fall toward the event horizon and beyond? Let's imagine you're in a spacecraft approaching a stellar mass black hole, say, 10 times the Sun's mass, with an event horizon about 30 kilometers in radius. You're still far away, perhaps 1,000 kilometers out, looking at the black hole against the starry background. What do you see? The black hole itself is utterly black, a perfectly dark circle silhouetted against space. But around it, the stars appear distorted. Light from stars behind or beside the black hole bends as it passes through the curved spacetime nearby. Stars near the edge of the black hole appear displaced from their true positions, creating a gravitational lensing effect. Directly behind the black hole, you might see a ring of light, the Einstein ring, where light from stars directly behind has been bent around the black hole to reach you. The entire starfield appears warped, compressed, and distorted around the black hole's silhouette. If the black hole has an accretion disk, you'd see a brilliant disk of glowing matter spiraling around the darkness. The inner parts of the disk, closest to the event horizon, would glow blue-white from extreme heat. The outer parts might glow red or orange. The disk wouldn't look like a simple flat circle because of relativistic effects. One side would appear brighter due to Doppler boosting. Matter moving toward you is blue shifted and brightened, while matter moving away is red shifted and dimmed. You'd also notice relativistic beaming, the tendency for radiation from fast-moving material to beam in its direction of motion. This makes the approaching side of the disk appear even brighter. The black hole's gravity bends light from the far side of the disk up and over, allowing you to see parts of the disk that would normally be hidden behind the black hole. The result is a complex, beautiful, and bizarre image, unlike anything in our everyday experience. As you continue approaching, you begin to feel the black hole's gravity. At 1,000 kilometers out from a 10 solar mass black hole, the gravity is noticeable but not extreme, comparable to Earth's gravity. You could easily escape with a rocket engine, but as you move closer, gravity strengthens rapidly. Gravity follows an inverse square law: get twice as close, feel 4 times the gravity. At 500 kilometers, gravity is 4 times stronger. At 250 kilometers, 16 times stronger. This rapid increase becomes critical as you approach the event horizon. At this point, something subtle but profound begins happening. Time starts to dilate, to slow down relative to distant observers. This is a consequence of general relativity. Strong gravitational fields slow time. Clocks closer to the black hole run slower than clocks farther away. If you're comparing your clock to one on a distant spacecraft, you'll notice their clock appears to run faster. They're experiencing more time per unit of your time. Conversely, to them, your clock appears to run slower. You're experiencing less time per unit of their time. This effect is small at first but grows stronger as you approach the event horizon. At the event horizon itself, time dilation becomes infinite. A distant observer would see your clock frozen, seeing you take infinite time to reach the horizon. But we're getting ahead of ourselves. We'll explore this paradox in detail later. You continue falling inward. Let's say you started from rest 1,000 kilometers out and simply let gravity pull you in with no engines firing. You accelerate as you fall, picking up speed. The black hole's gravity does work on you, converting gravitational potential energy into kinetic energy. By the time you've fallen to 100 kilometers out, you're moving at a significant fraction of light speed. By 50 kilometers, you might be moving at 10 or 20% of light speed. The exact numbers depend on your starting point and the black hole's mass, but the key point is clear: you accelerate to relativistic speeds. These high speeds create additional effects. The starlight ahead of you becomes blue shifted due to the Doppler effect, compressed to shorter wavelengths and higher energies. Starlight behind you red shifts. This would create a rainbow effect if you could see all wavelengths. Optical light from ahead shifts into the ultraviolet. Infrared from ahead shifts into visible light. The cosmic microwave background radiation from ahead shifts into infrared and visible light. Meanwhile, light from behind shifts to longer wavelengths. Visible light becomes infrared. Infrared becomes microwave. The effect intensifies as you accelerate. Eventually, the universe ahead would glow with blue shifted radiation, while the universe behind fades and redshifts into darkness. But there's another effect aberration. Just as rain appears to come from ahead when you're driving, light aberrates in your direction of motion when you're moving at high speed. Stars ahead of you appear to cluster together in your forward direction. Stars behind spread out. At very high speeds approaching light speed, almost all the stars in the sky would appear compressed into a bright spot ahead of you. These visual effects would be stunning. The black hole ahead appears as an expanding darkness. The accretion disk, if present, forms complex shapes due to gravitational lensing, Doppler effects, and relativistic beaming. Stars swirl and distort. The universe ahead brightens and compresses while the universe behind dims and spreads. At the same time, you begin to feel tidal forces. Tidal forces arise because gravity is stronger, closer to the black hole. If you're falling feet first, your feet are closer to the black hole than your head, so they experience stronger gravity. This difference stretches you. Far from the event horizon, tidal forces are negligible, but as you approach, they grow. The strength of tidal forces increases with the cube of proximity. Get twice as close, experience 8 times the tidal force. This rapid increase means tidal forces become extreme, very close to the event horizon for stellar mass black holes. For a 10 solar mass black hole, the tidal forces become lethal well before you reach the event horizon. At perhaps a few hundred kilometers out, 10 times the event horizon radius, the differential gravity between your head and feet would already be uncomfortable. By the time you reached 100 kilometers, 3 times the event horizon radius, the tidal forces would be pulling you apart. This process has been nicknamed spaghettification, because you'd be stretched like a strand of spaghetti. Your body would elongate along the radial direction, the direction toward the black hole, and compress in the perpendicular directions. The same amount of mass stretched into a longer, thinner shape. The stretching wouldn't be gentle. Tidal forces would overwhelm the molecular bonds holding your body together. Your tissues would tear, your bones would snap, your cells would rupture. You'd be pulled into a stream of atoms, then perhaps into subatomic particles as you approached closer. For a stellar mass black hole, spaghettification would kill you well before you reached the event horizon. You'd die in agony, stretched and torn apart by tidal forces, while still outside the point of no return. Your remains would continue falling inward, further stretched and shredded, until finally crossing the event horizon as a thin stream of particles. But here's a crucial point. The strength of tidal forces at the event horizon depends on the black hole's mass. Tidal force at a given location depends on the curvature of space-time there, which depends on how concentrated the mass is. For a stellar mass black hole, the mass is concentrated within a small event horizon, creating extreme curvature and extreme tidal forces. For a supermassive black hole, the situation is different. A billion solar mass black hole has an event horizon about 3 billion kilometers in radius, roughly the distance from the Sun to Uranus. At this event horizon, despite the enormous mass, the tidal forces are actually quite gentle because the mass is spread out over such a large volume in terms of the space-time curvature. If you were falling into a supermassive black hole, you could cross the event horizon without being torn apart. The tidal forces at the horizon would be survivable, perhaps even barely noticeable, depending on the black hole's mass. You'd pass through the point of no return intact, still alive, still conscious, still able to experience whatever lies beyond. This is one of the strangest aspects of black holes. For stellar mass black holes, you die before crossing the horizon from tidal forces. For supermassive black holes, you might survive crossing the horizon only to face whatever awaits inside. Let's assume, for our journey, that you're falling into a supermassive black hole large enough that tidal forces at the event horizon are survivable. This allows us to explore what happens beyond the point of no return, an experience impossible with stellar mass black holes. As you approach the event horizon, time dilation becomes more severe. Your clock, compared to distant observers, runs slower and slower. Radiation from the universe around you becomes more intensely blue-shifted ahead and red-shifted behind. The black hole's apparent size grows, filling more and more of your view. If the black hole is rotating a Kerr black hole, there's an additional region outside the event horizon called the ergosphere. In the ergosphere, space-time itself is dragged around the black hole by its rotation. You cannot remain stationary relative to distant stars. Space-time carries you around the black hole. You could still escape from the ergosphere by firing rockets, but you'd be rotating around the black hole as you did so. The boundary of the ergosphere is called the static limit, the closest distance where you could, in principle, remain static relative to distant stars. Inside the static limit, but outside the event horizon, you're forced to rotate with space-time, but can still escape. For our journey, let's imagine the black hole is non-rotating to keep things simpler. You're falling straight toward the event horizon. The darkness ahead expands. Time dilates. Tidal forces grow but remain survivable. Your speed approaches light speed, and then, in your reference frame, after falling for a finite amount of time, you reach the event horizon. You cross the point of no return. What happens next? You've reached the event horizon. In your own experience, this moment is not particularly special. There's no sign, no barrier, no sensation of passing through anything. The event horizon is not a physical surface, but merely a mathematical boundary in space-time. You cross it the way you might cross the equator, unaware of the exact moment unless you're watching instruments. Your instruments, if you have them, might register the crossing. A GPS-like system, triangulating your position relative to distant stars, would show you've passed the Schwarzschild radius, but you'd feel nothing unusual at that instant. The acceleration, you feel the tidal forces stretching you, changes smoothly and continuously. There's no discontinuity at the horizon. Looking outward, away from the black hole, you'd still see the universe. Light can still reach you from outside, traveling inward across the event horizon. The stars remain visible, though heavily distorted by relativistic effects and gravitational lensing. The view continues to blue shift and aberrate forward as you accelerate. The light reaching you from outside carries information about events happening in the external universe. But because of the extreme time dilation, events that take years or centuries outside might appear to happen in seconds or minutes from your perspective inside the horizon. You might witness the rapid aging of the cosmos stars, evolving through their life cycles, supernovae flashing, galaxies rotating noticeably. This effect depends on your exact trajectory and the black hole's properties, but the principle holds. Time outside runs faster relative to you inside. If you could survive long enough and observe carefully, you might see the distant future of the universe compressed into your final moments. Civilizations could rise and fall, stellar populations could turn over, cosmic evolution could play out at accelerated speed. The blue shifting of incoming light means that longer wavelengths compress into shorter ones. Radio waves from outside blue shift into microwaves. Microwaves blue shift into infrared. Infrared becomes visible light. The cosmic microwave background, normally invisible at 2.7 Kelvin temperature, blue shifts into visible or even ultraviolet light, making the sky glow with compressed ancient light from the Big Bang. Looking toward the black hole deeper inward, you see only darkness. No light comes from beyond your position moving outward, because everything inside the event horizon is falling toward the singularity, including light. The inward direction is utterly black. But here's the profound change you can no longer escape. Before crossing the horizon, you could fire powerful rockets and reverse course, escaping to the outside universe given sufficient thrust. After crossing, no amount of thrust can save you. You could fire the most powerful rockets imaginable, enough to accelerate you to 99% of light speed in the outward direction, and you'd still be falling inward toward the singularity. This defies intuition completely. How can you be moving outward at nearly light speed yet still falling inward? The answer requires understanding how space-time works inside the event horizon. Outside, space-time has a normal structure where time and space behave as expected. Time flows forward, space extends in all directions, and you can move through space while time carries you forward. Inside the event horizon, this familiar structure is inverted in a profound way. The radial direction, the direction toward or away from the singularity, becomes time-like rather than space-like. What does this mean? Outside the black hole, you cannot choose which direction to move in time. Time carries you forward from past to future inexorably. You can move left or right, up or down, forward or backward in space, but not backward in time. Inside the black hole, the inward radial direction becomes like time, Just as you cannot stop time from carrying you from past to future outside, you cannot stop the inward radial direction from carrying you toward the singularity inside. The singularity is not a place in space ahead of you, it's a moment in your future, approaching as inevitably as tomorrow. When you fire your rockets outward, you're not trying to move to a different place, you're trying to move to a different time, which is impossible. The rockets can change your trajectory through space, can slow your fall or speed it up, but they cannot prevent you from moving forward through the time-like radial coordinate toward the singularity. This strange inversion of space and time is what makes the event horizon a true point of no return. It's not that gravity is too strong to escape, though it is. It's that the very structure of space-time has changed so that outward is no longer a meaningful spatial direction. All directions lead to the singularity, just as all moments lead to the future. This seems paradoxical. How can moving outward at 99% of light speed still be falling inward? The answer lies in the structure of space-time itself inside the event horizon. Space and time exchange roles in a sense. Outside the black hole, time flows forward inexorably. You cannot choose to move backward in time, but you can choose spatial direction. You can move left, right, forward, backward, up, down. Inside the event horizon, this reverses. The inward spatial direction toward the singularity becomes time-like. Just as you cannot avoid moving forward in time outside, you cannot avoid moving inward spatially inside. The singularity is not a place in space you move toward, it's a moment in your future you inevitably reach. This is difficult to visualize because our intuition is built on normal space-time. Inside the event horizon, space-time is so severely curved that its structure becomes alien to everyday experience. All future-directed paths, all possible trajectories lead to the singularity. You can no more avoid reaching the singularity than you can avoid reaching tomorrow. It's in your future, unavoidable, regardless of what you do. How long until you reach the singularity? This depends on the black hole's mass. For a stellar mass black hole of 10 solar masses, once you cross the event horizon, you'd reach the singularity in about a 10,000th of a second. The journey from horizon to singularity is very brief, less time than a blink of an eye. For a supermassive black hole, the time is much longer. A billion solar mass black hole gives you hours from horizon to singularity. A black hole of 4 million solar masses, like Sagittarius A star, gives you about 10 seconds. You'd have 10 seconds after crossing the point of no return before reaching the singularity where space-time curvature becomes infinite and you're destroyed. During this brief time, what do you experience? The tidal forces continue to grow. Remember, tidal forces increase as you approach the singularity. Even for a supermassive black hole where tidal forces at the event horizon were gentle, they grow rapidly as you fall further inward. By the time you're halfway from the horizon to the singularity, tidal forces might be uncomfortable. By the time you're 90% of the way, they might be painful, stretching and compressing you significantly. In the final moments before reaching the singularity, tidal forces grow infinite. You're stretched infinitely in the radial direction, compressed infinitely in the perpendicular directions, and torn apart at the most fundamental level. But before that final destruction, during those seconds or hours of falling inside the event horizon, what do you see? This is where things become speculative, because no human can survive the journey, and we have no direct observations. We must rely on general relativity's predictions. Looking outward, toward where you came from, you'd still see the universe. Light from outside can reach you, traveling inward faster than you're falling. You'd see the stars, heavily blue-shifted now, compressed by aberration. Due to extreme time dilation effects, you might see the universe outside evolving rapidly. Events that take years outside might appear compressed into moments for you. Some calculations suggest you might see the entire future history of the universe flash before you in your final moments. Stars would be born, evolve, and die. Galaxies would merge. The universe outside would age billions of years in the seconds or hours you have left. This is speculative and depends on details of exactly how the light reaches you, but it's one possible consequence of the extreme time dilation. Looking inward, you see only darkness, the singularity approaching. No light comes from the singularity itself because, well, it's a singularity, a point where space-time curvature diverges. What would a singularity look like? We don't know. Our physics breaks down there. As you fall, the black hole's interior structure remains mysterious. General relativity predicts that, inside the event horizon, space-time continues to exist in some form, becoming increasingly curved as you approach the singularity. But quantum effects, which general relativity ignores, must become important at some point. Quantum gravity, a theory we don't yet have, would be needed to describe the singularity itself. Some physicists speculate that quantum effects might prevent the singularity from being truly infinite. Perhaps matter and energy, including you, undergo some kind of quantum transition before reaching the classical singularity. Perhaps space-time itself becomes grainy or discrete at scales smaller than the Planck length. Perhaps the singularity is replaced by a Planck scale region where unknown physics operates. But these are speculations. Based on general relativity alone, the singularity is real. You reach it in finite proper time after crossing the horizon, and when you reach it, tidal forces become infinite and you're destroyed absolutely. Every atom of your body, every particle, crushed and torn to an unknown fate. This is the ultimate one-way journey. You cross the event horizon, a point of no return where your fate is sealed. You fall inexorably toward the singularity, experiencing the final seconds or hours of existence. You witness the universe outside perhaps accelerating through its entire future. And then you reach the singularity, where physics as we know it ends. But there's more to explore. What about the observers watching you fall? What do they see? While you experience crossing the event horizon and reaching the singularity in finite time, observers far from the black hole see something completely different. This divergence, you experiencing one thing, them seeing another, is one of the most profound aspects of black holes. Let's set the scene. You're falling toward the black hole while a friend watches from a safe distance, say 1,000 kilometers away, hovering with rockets keeping them stationary. As you fall, your friend watches you through a telescope. At first, they see you accelerating normally. You fall faster and faster, appearing to speed up as the black hole's gravity accelerates you. Light from your suit, or from a lamp you're carrying, travels outward to their telescope. But as you approach the event horizon, something strange happens from your friend's perspective. You appear to slow down. Your acceleration, which had been increasing, seems to decrease. You're still moving inward, but more and more slowly from their viewpoint. This is time dilation in action. As you get closer to the event horizon, time for you, as measured by your friend's clock, slows down. They see you experiencing time more slowly. Actions that take 1 second by your clock take increasingly long by their clock. As you approach closer to the horizon, this effect intensifies. When you're at twice the event horizon radius, you appear to be running at about 70% normal speed from their viewpoint. At 1.5 times the radius, about 60% speed, at a tiny distance above the horizon, you appear nearly frozen. From your friend's perspective, you never actually reach the event horizon. They see you getting closer and closer, slower and slower, asymptotically approaching but never quite arriving. They would have to wait infinite time, literally forever, to see you cross the horizon. At the same time, light from you becomes increasingly redshifted. Light climbing out of the deep gravitational well near the event horizon loses energy, shifting to longer wavelengths. Visible light from your suit shifts to infrared, then to microwaves, then to radio waves, becoming increasingly faint. The light also becomes dimmer because of time dilation. If you're flashing a light once per second by your clock, your friend sees the flashes coming slower and slower by their clock. Fewer photons arrive per unit time. Combined with redshifting, this makes you fade from view. Within seconds or minutes of your approach to the horizon, as measured by your friend's clock, you become too dim to see. You redshift into invisibility, appearing frozen just above the event horizon. Fading to black, you never appear to cross the horizon from their perspective. So here's the paradox. By your clock, you reach and cross the event horizon in finite time, seconds, minutes, or hours, depending on the trajectory and the black hole's mass. You experience this crossing, continue falling inward, and reach the singularity. By your friend's clock, you never cross the horizon. You appear frozen just above it, fading away, remaining there forever. They could wait billions of years, and they still wouldn't see you cross. From their reference frame, you're eternally frozen at the horizon. Both perspectives are valid. This isn't a contradiction, but rather a deep feature of general relativity. Space-time events are observer-dependent. Whether the horizon crossing has happened depends on the reference frame. For you, the infalling observer, the horizon crossing is in your past after you've crossed. It's an event you've experienced. For the distant observer, the horizon crossing is infinitely far in the future, an event they'll never see occur. This has strange implications. Imagine you're falling in, and as you cross the horizon, you fire a powerful laser back toward your friend. What do they see? They never see the laser light because it's emitted from inside the horizon. Light emitted inside cannot escape. From their perspective, they see you fading away, and any light you emit near the horizon becomes infinitely redshifted and delayed, never arriving at any finite time. From your perspective, you fire the laser. You see the light traveling outward. But that light doesn't escape either. It's inside the event horizon, falling toward the singularity just like you, despite traveling outward at light speed. Another thought experiment. Suppose your friend decides to rescue you. After seeing you approach the horizon and fade from view, they fire rockets and dive in after you. What happens? From your perspective, you've already crossed the horizon and are falling toward the singularity. If your friend dives in soon enough, they can cross the horizon and catch up with you before you reach the singularity. You could even reunite inside the black hole, spend your final moments together before tidal forces tear you apart and you both hit the singularity. From an outside observer's perspective, watching both of you, neither of you ever crosses the horizon. Both of you appear frozen at the horizon. You first, then your friend, both fading to invisibility. The outside observer sees both of you hanging there forever. This resolution of reference frames is consistent but deeply weird. Events that have happened in one reference frame haven't happened in another. The horizon crossing is an event with observers on both sides, you inside, your distant friend outside, but they disagree on whether it's occurred. This raises questions about the nature of reality. If you're inside and have crossed the horizon, but observers outside never see you cross, in what sense has the crossing happened? Is the event real if some observers never witness it? General relativity's answer is that all reference frames are equally valid. The crossing is real in your reference frame. It's also true that in the distant observer's frame, they never see it happen. Both statements are correct simultaneously. Reality is frame-dependent. This becomes even stranger when we consider the black hole's lifetime. Hawking radiation means black holes slowly evaporate, losing mass and eventually disappearing entirely. For stellar mass black holes, this takes impossibly long, 10 to the 67 years or so. For supermassive black holes, even longer. But eventually, the black hole evaporates completely. From the distant observer's perspective, you're hanging frozen at the event horizon for all those eons. Then, as the black hole evaporates, the event horizon shrinks. What happens to you? This is the black hole information paradox, which we'll explore in more depth later. The puzzle is that you appear to be frozen at the horizon forever from the outside perspective, yet the black hole eventually evaporates. How can you both be frozen there and also fall in? For now, the key point is that falling into a black hole creates a fundamental split in reference frames. Your experience crossing the horizon, falling to the singularity, is finite and definite. The distant observer's experience, seeing you frozen and fading, is also definite but completely different. Both are true, neither is privileged, and this is just how general relativity works, near event horizons. We've mentioned tidal forces and spaghettification, but let's explore this in more visceral detail. What exactly happens to your body as these forces grow? Tidal forces arise from the gradient in gravitational field strength. Your feet, being closer to the black hole, experience stronger gravity than your head. This difference creates a stretching force along your body. Simultaneously, there's a squeezing force perpendicular to the radial direction. To understand why, imagine falling feet first. Your feet pull more strongly toward the black hole's center than your head, but your left and right sides also pull toward the center. If you draw lines from your left shoulder and right shoulder toward the singularity, those lines converge. This convergence creates a compressive force, squeezing you from the sides. The result is stretching along the radial direction and compression perpendicular to it. As you fall, you become longer and thinner, like a noodle or strand of spaghetti, hence spaghettification. For a stellar mass black hole, let's calculate what this feels like. Suppose you're 2 meters tall, falling into a 10 solar mass black hole. When you're at a distance of about 300 kilometers, 10 times the event horizon radius, the differential gravity between your head and feet creates a force of roughly 1% of Earth's gravity. Uncomfortable, but survivable. At 150 kilometers, the tidal force is about 10% of Earth's gravity. This would be painful, like someone pulling your head and feet in opposite directions with the force of about 10 kilograms on each. At 75 kilometers, The force is about 40% of Earth's gravity. This would be excruciating. Your spine would be under tremendous stress. Discs between vertebrae would herniate. Blood flow would be disrupted as vessels stretched. At about 50 kilometers, less than twice the event horizon radius, the tidal force would be around 100% of Earth's gravity. Your head and feet would each feel a force roughly equal to your body weight pulling in opposite directions. Your spine would snap, blood vessels would rupture. You'd be in agony. At 35 kilometers just above the event horizon, the tidal force would exceed 10 times Earth's gravity. Your body would literally tear apart. Muscles, tendons, ligaments, all would fail. Your torso would separate from your legs. Your head would separate from your torso. Each piece would continue falling separately, each experiencing its own further stretching. As the pieces fall closer, they stretch further. Limbs tear into fragments. Fragments tear into tissues. Tissues tear into cells. Cells rupture into molecules. Molecules break into atoms. Eventually, even atoms might be pulled apart into nuclei and electrons. All of this would happen before you reached the event horizon for a stellar mass black hole. You'd be dead, thoroughly destroyed while still technically outside the point of no return. Your remains, now a thin stream of particles, would continue falling inward, crossing the event horizon and proceeding to the singularity. The compression perpendicular to the radial direction would be equally devastating. Your body would be squeezed from the sides, ribs would crack, organs would be crushed. The circumference of your body would shrink as the length increased. The net effect is that your volume remains roughly constant, initially stretched one way, compressed the other, but the shape becomes increasingly elongated. A rough sphere becomes an ellipsoid, then a cylinder, then a thread, then a stream of particles. For a supermassive black hole, the situation differs dramatically. Tidal forces at the event horizon scale inversely with the square of the black hole's mass. A billion solar mass black hole has tidal forces at its event horizon that are 10,000 billion times weaker than a 10 solar mass black hole. At the event horizon of such a supermassive black hole, the tidal force on a 2-meter human would be utterly negligible, far less than the tidal force you experience on Earth from the moon's gravity. You could cross the horizon intact, alive, and comfortable. But don't relax. Tidal forces grow as you fall inward from the horizon toward the singularity. They scale with distance cubed, so they increase rapidly. For a billion solar mass black hole, you might have hours from horizon to singularity, but in the final minutes, tidal forces would become severe. Let's imagine that journey. You cross the horizon, feeling nothing unusual. You spend the first hour falling, perhaps looking around, marveling at the strange views. Tidal forces are present but gentle, like stretching slightly. In the second hour, tidal forces become more noticeable. You feel a persistent pulling sensation, head to feet. It's uncomfortable but not yet painful, like being on a medieval rack set to a low tension. In the third hour, pain begins. Your spine aches. Your limbs hurt. Blood pressure changes as vessels stretch. You might experience headaches, nausea, difficulty breathing as your torso elongates. With perhaps 30 minutes left, the pain becomes severe. You're being stretched noticeably. Your height has increased by a centimeter, then 5, then 10. Your body's proportions become visibly wrong. Joints dislocate, bones crack under the stress. With 10 minutes left, you're in agony. Your body has stretched by dozens of centimeters. Skin tears, blood vessels rupture, organs fail. You're conscious, but in the worst pain imaginable. With 1 minute left, your body is no longer recognizably human. You've stretched to perhaps 3 or 4 meters long, thin and distorted. Consciousness might fail from trauma and blood loss. Structural integrity is completely gone. In the final seconds, what remains of you tears into pieces, then fragments, then particles, and then you reach the singularity, where tidal forces become infinite in the final infinitesimal instant. This assumes you remain alive throughout, which is doubtful. Shock, blood loss, organ failure, any of these would likely kill you well before the singularity. But however you die, your body continues to experience ever-increasing tidal forces until final destruction. There's a grimly fascinating detail about the orientation of your fall. If you fall feet first, your feet are torn off first. If you fall head first, your head is torn off first. If you could somehow orient yourself perpendicular to the radial direction, lying sideways as you fall, you'd experience less stretching momentarily. But the convergent nature of the field would reorient you radially and then stretch you just as much. No orientation saves you. No position helps. Tidal forces are inescapable consequences of gravity's gradient, and near a singularity, gradients become extreme. Could you survive with technology? A sufficiently strong spaceship might resist tidal forces that would destroy a human body. The ship would need to be built of materials far stronger than anything we have, perhaps exotic matter held together by forces we haven't discovered. But even the strongest conceivable materials would fail eventually, as tidal forces grow infinite near the singularity. You might survive longer in a ship, perhaps reaching closer to the singularity before destruction, but the end result is the same total annihilation. This is the visceral reality of falling into a black hole. It's not a gentle journey into the unknown. It's a brutal, painful, inevitable destruction by forces that grow without bound, tearing apart everything: body, ship, atoms, perhaps even spacetime itself, as you approach the mathematical singularity where physics breaks down. So far, we've discussed non-rotating black holes, Schwarzschild black holes, but most black holes in nature probably rotate, formed from collapsing stars that had angular momentum. Rotating black holes, Kerr black holes, have different, and even stranger, internal structures. A rotating black hole has 2 event horizons, an outer event horizon and an inner event horizon. The outer horizon is the point of no return we've discussed. The inner horizon is deeper inside, closer to the singularity. Between these 2 horizons is a region where some truly bizarre physics occurs. The outer event horizon of a rotating black hole is smaller than for a non-rotating black hole of the same mass. Rotation reduces the event horizon radius. For a maximally rotating black hole, one spinning as fast as theoretically possible, the outer horizon radius is about half the radius of a non-rotating black hole. Outside the outer horizon is the ergosphere, which we mentioned earlier. In the ergosphere, space-time is dragged around by the black hole's rotation. You cannot remain stationary. You're forced to rotate with space-time. This rotation is called frame dragging. The boundary of the ergosphere, the static limit, is larger than the outer event horizon. Between the static limit and the outer horizon, you're forced to rotate but can still escape if you fire rockets outward. Once you cross the outer horizon, escape becomes impossible, just as with a non-rotating black hole. But inside the outer horizon of a rotating black hole, the structure is different. You're not immediately doomed to the singularity. Instead, there's a possibility, at least mathematically, of avoiding it. The singularity in a rotating black hole is not a point but a ring. It's a circle in space, like a smoke ring, with the black hole's rotation axis passing through its center. If you approach this ring singularity from certain angles, the mathematics of general relativity suggests you might pass through the ring without being destroyed. This seems impossible. How can you pass through a singularity, a region of infinite curvature, and survive? The answer is that you wouldn't pass through the singularity itself, but through the opening in the ring. The singularity forms a loop, and the interior of the loop is, mathematically at least, a region of finite curvature. If you could navigate through the ring, you'd emerge into a bizarre region of spacetime. According to the Kerr metric, the solution to Einstein's equations for rotating black holes on the other side of the ring singularity, there's another region of spacetime. This region might be another universe, or a different part of our own universe, or a different time in our universe. Some solutions suggest that the rotating black hole interior contains closed time-like curves, paths through spacetime that loop back on themselves, allowing time travel. You could, in principle, travel into your own past by navigating through the black hole interior. This all sounds like science fiction, and indeed, most physicists are skeptical that these features represent physical reality. The Kerr solution is mathematically valid, but likely physically unrealistic inside the event horizon for several reasons. First, the Kerr solution assumes a perfectly eternal rotating black hole, one that has existed forever and will exist forever, with no matter falling in. Real black holes form from collapsing stars and accrete matter. These processes likely change the internal structure significantly. Second, there's the problem of the inner event horizon. As you cross the outer horizon and fall toward the inner horizon, something devastating happens. All the light and matter that ever fell into the black hole, compressed by gravitational time dilation, piles up at the inner horizon. From the perspective of an infalling observer, reaching the inner horizon means encountering the entire history of infalling radiation and matter blue-shifted to infinite energy. This creates a mass inflation scenario where the energy density becomes infinite, likely replacing the inner horizon with a violent singularity that destroys anything trying to cross. This means the inner horizon is probably unstable. The neat mathematical structure of the Kerr solution, with its traversable ring singularity and exotic regions beyond, likely doesn't exist in any real black hole. Instead, instabilities and accumulated matter create a more chaotic, destructive interior. Third, quantum effects almost certainly become important. The Kerr solution is purely classical general relativity, ignoring quantum mechanics. Near the Planck scale, the realm where quantum gravity would operate, the smooth space-time of general relativity likely breaks down into something more complex. Most physicists believe that the true interior of a rotating black hole is not described by the Kerr solution alone. Quantum gravity effects, mass inflation at the inner horizon, and the chaotic dynamics of infalling matter probably create a scenario where you're still destroyed before reaching the ring singularity. But we don't know for certain. The interior of a rotating black hole remains one of the great unknowns in physics. Perhaps there are exotic possibilities. Perhaps traversing the interior is possible under certain conditions. Perhaps the ring singularity is real and offers a gateway to elsewhere. For the sake of imagination, let's consider what it might be like if you could navigate the interior. You cross the outer event horizon, just as with a non-rotating black hole. But instead of heading straight toward a point singularity, you maneuver toward the ring. The journey requires precise navigation. Tidal forces are present, though they might be different in structure due to the rotation. You'd need to approach the ring from the right angle through its opening rather than into the ring itself. As you approach the inner horizon, you encounter the accumulated radiation. If mass inflation hasn't destroyed the structure, this radiation might be intense but survivable if you're moving fast enough that you pass through before being cooked. You pass the inner horizon. Space-time structure becomes even more bizarre. You're now in a region where closed time-like curves might exist. Causality becomes ambiguous. You might see images of your own future self, or your past self, or multiple versions of yourself at once. Approaching the ring singularity, you pass through the opening. And then, what? Do you emerge into another universe? Do you find yourself in a different region of space-time? Do you encounter exotic physics we can't even imagine? The honest answer is, we don't know. The mathematics allows these possibilities, but physics might forbid them. The only way to know for certain would be to fall into a rotating black hole and report back, which, of course, is impossible. Most likely, the reality is less exotic and more destructive. You cross the outer horizon, fall toward the inner horizon, encounter mass inflation instabilities that destroy you, and never reach the ring singularity. The fantasy of traversing a black hole to reach another universe probably remains just that, a fantasy. But the fact that the mathematics of general relativity even allows such possibilities is remarkable. It suggests that black holes, already among the strangest objects in existence, might be stranger still than we currently understand. When you fall into a black hole, what happens to the information about you? This question leads to one of the deepest puzzles in theoretical physics, the black hole information paradox. In quantum mechanics, information is fundamental. The complete quantum state of a system contains all information about that system. Crucially, quantum mechanics is deterministic. Knowing the complete state now allows you to predict the complete state at any future time and retrodict it at any past time. Information is never lost. It's only scrambled or hidden. This is formalized in the principle of unitarity. Quantum evolution is unitary, meaning the total information content of a closed system remains constant over time. Even if a book burns, the information about the book's contents still exists in the ashes, smoke, and radiation scrambled beyond practical recovery, but theoretically present. Now consider what happens when you fall into a black hole. You carry information, the arrangement of every particle in your body, your quantum state. You cross the event horizon and fall to the singularity, where you're destroyed. From the outside perspective, you appear frozen at the horizon, fading from view. Over eons, the black hole slowly evaporates via Hawking radiation. Eventually, it evaporates completely, leaving only thermal radiation. Here's the problem. Hawking radiation is thermal random, described by temperature alone. It carries no information about what fell into the black hole. Whether the black hole formed from hydrogen or iron, absorbed books or rocks, the Hawking radiation is the same, determined only by the black hole's mass, charge, and spin. If the black hole evaporates completely into thermal radiation, where did the information about you go? It seems to have been destroyed. You fell in carrying information. The black hole evaporates into featureless radiation, and the information is gone. But this violates unitarity. Information cannot be destroyed in quantum mechanics. So we have a paradox. General relativity says you fall into the black hole and are destroyed, with no information escaping. Quantum mechanics says information cannot be destroyed. Something has to give. This is the black hole information paradox, formulated by Stephen Hawking in the 1970s. It's remained one of the most challenging problems in theoretical physics for decades. Proposed solutions fall into several categories. One possibility: information is not destroyed, but is encoded in the Hawking radiation in subtle correlations. The radiation appears thermal locally, but contains hidden information in global correlations between particles. As the black hole evaporates, this information is gradually released. The problem is that calculations seem to show the information comes out too slowly. By the time most of the black hole has evaporated, the information about early infalling matter still hasn't emerged. This creates the firewall paradox. The firewall paradox goes like this. If information is encoded in Hawking radiation, then particles emitted late in the evaporation must be entangled with particles emitted early to carry out the information. But quantum mechanics limits how many things a particle can be entangled with. The late emitted particles must be entangled with the early radiation to carry information, and also with their partners just inside the horizon to create the smooth horizon predicted by general relativity. This double entanglement is impossible. The resolution might be that the smooth horizon doesn't exist. Instead, there's a firewall of high-energy particles right at the horizon that destroys anything trying to cross. This would mean you don't smoothly cross the horizon, but are incinerated instantly at the boundary. The equivalence principle, the idea that freely falling observers experience no unusual forces, would be violated at the horizon. Many physicists find this unsatisfying. The equivalence principle is fundamental to general relativity. Violating it means giving up one of our deepest physical insights. But preserving it seems to require violating unitarity, which is equally fundamental to quantum mechanics. Another possibility: information is stored in remnants. When the black hole evaporates to near Planck mass, quantum gravity effects halt the evaporation, leaving a tiny remnant that stores all the information that fell in. The problem is that this seems to require the remnant to have infinite internal states, which creates its own paradoxes. A third possibility: information escapes through wormholes or baby universes. The black hole interior connects to another region of spacetime, and information leaks out through this connection. This is highly speculative and requires exotic features we have no evidence for. A fourth possibility: the holographic principle. This idea suggests that all the information about the black hole's interior is encoded on its event horizon like a hologram. The three-dimensional interior is fundamentally a two-dimensional encoding on the boundary. When the black hole evaporates, it's the boundary that evaporates, releasing the encoded information. This approach has led to important insights but hasn't fully resolved the paradox. Recent developments involve ideas from quantum entanglement and space-time connectivity. Some physicists propose that entanglement between particles creates the geometry of space-time itself. ER equals EPR, connecting Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs. Entangled particles. In this view, the black hole interior and exterior are connected by quantum entanglement in ways we're only beginning to understand. For you, falling into the black hole, the paradox is academic. You experience falling in, being destroyed, reaching the singularity. The information about you might be encoded in Hawking radiation in 50 billion years, but that doesn't help you now. From the outside perspective, the paradox is real and pressing. If black holes destroy information, quantum mechanics is wrong. If information escapes, it must do so in ways we don't yet understand, requiring new physics. The information paradox hints that our understanding of black holes is incomplete. Either general relativity needs modification, or quantum mechanics does, or our understanding of how they fit together needs fundamental revision. This brings us to a deeper question. What is the black hole interior really like? Is it described accurately by general relativity, or do quantum effects create something completely different? General relativity predicts that the black hole interior contains a singularity, a point or ring where space-time curvature becomes infinite, but at such extreme scales, quantum effects must become important. What does quantum mechanics say about the singularity? The short answer is we don't know. We don't have a complete theory of quantum gravity, a framework that unifies quantum mechanics and general relativity. Without such a theory, we can't reliably describe what happens at the singularity or even whether singularities exist in the quantum theory. Several approaches to quantum gravity offer hints. Let's explore them. String theory suggests that fundamental particles are not point-like but tiny vibrating strings. At normal scales, strings appear point-like because they're so small around the Planck length, about 10 to the minus 35 meters. But near a singularity, where curvature becomes extreme on tiny scales, the stringy nature matters. In string theory, as you approach what would classically be a singularity, space-time smooths out. The infinite curvature is replaced by high but finite curvature. The singularity is resolved, eliminated by the extended nature of strings. Instead of a point of infinite density, there's a Planck scale region of very high but finite density. What happens if you reach this region? You might be crushed to incredibly high density but not infinitely. Your particles, themselves composed of strings, might undergo transitions into different vibrational modes. Matter might be converted into more fundamental string states, but you wouldn't experience infinite forces, just extremely large ones. This doesn't save you. Even finite but enormous forces would destroy you completely. But it's less pathological than classical infinity. And it might mean that information is not lost at the singularity, but transformed in ways that preserve unitarity. Loop quantum gravity takes a different approach. In this theory, space-time itself is quantized. Space is made of discrete chunks at the Planck scale, like pixels in an image. When you try to compress matter to infinite density, quantum effects prevent it. Loop quantum gravity predicts that as a black hole forms and matter collapses, it doesn't reach a singularity. Instead, it bounces. The collapsing matter reaches a maximum density high but finite, and then rebounds. This creates a white hole on the other side, where matter explodes outward. If this is correct, falling into a black hole might mean emerging from a white hole in another region of space-time, perhaps another universe, or a different time in our universe. The black hole interior becomes a tunnel connecting black and white hole regions. But loop quantum gravity is incomplete and makes predictions that are difficult to test. The bounce scenario is intriguing but speculative. Another approach involves the holographic principle and adds CFT correspondence. The holographic principle suggests that the physics of the black hole interior is encoded on its event horizon. The interior is emergent from the boundary description, like a hologram creating a three-dimensional image from two-dimensional information. In this view, asking what happens at the singularity might be asking the wrong question. The singularity might not exist as a physical entity, but as an artifact of trying to describe the interior in three-dimensional terms when it's fundamentally two-dimensional information on the horizon. This is highly abstract and doesn't give a clear picture of what you'd experience falling in, but it suggests that the classical singularity is not the final word. Some physicists propose that quantum effects create a firewall at the event horizon, as mentioned earlier. If so, you never reach the singularity because you're incinerated at the horizon by high-energy quantum radiation. The interior might not exist as a separate region at all. Another idea is that the black hole interior is a complex quantum state, a superposition of many possibilities. When you fall in, you become entangled with this state. Your information isn't destroyed, but spreads out across the quantum state of the black hole. When the black hole evaporates, the information is released through subtle correlations in the Hawking radiation. What would this feel like? Probably like being destroyed at the singularity, because the macroscopic classical experience you as a conscious observer can't persist through such extreme quantum entanglement. But at the quantum level, your information persists. The honest answer is that we're speculating. Without a tested theory of quantum gravity, we can't say definitively what happens at the singularity. We know that classical general relativity predicts infinite curvature and tidal forces. We suspect that quantum effects modify this, probably eliminating the classical singularity. But we don't know what replaces it. A bounce? A Planck scale region of finite curvature? A breakdown of spacetime into discrete quantum geometry? A transformation into exotic string states? Or something we haven't imagined? This uncertainty is frustrating, but also exciting. Black holes serve as natural laboratories for quantum gravity. The interior, inaccessible though it is, represents a regime where quantum gravity must operate. Understanding black holes fully requires understanding quantum gravity. Progress is being made. Insights from holography, entanglement, and string theory are reshaping how we think about black holes. The information paradox, once considered intractable, now has several promising approaches to resolution. In the coming decades, we might develop a complete theory of quantum gravity. When we do, one of its first applications will be describing black hole interiors and singularities. We'll finally know what happens when you fall in. Until then, the singularity remains a mystery, a place where our best physics fails, where space-time as we know it ends, where the ultimate fate of matter, energy, and information is uncertain. Not all black holes are the same. We've discussed stellar mass and supermassive black holes. Let's explore how the experience of falling in differs for various types. Stellar mass black holes, formed from collapsing stars, typically have masses between 3 and 20 times the Sun's mass. Their event horizons are correspondingly small radii, from about 9 to 60 kilometers. The tidal forces at the event horizon are enormous. You'd be spaghettified long before crossing, dying in agony tens or hundreds of kilometers out. Your remains would cross the horizon as a stream of particles. From horizon to singularity takes milliseconds. The journey is brief, violent, and utterly destructive. If such a black hole has an accretion disk, your approach would involve intense radiation. The disk glows from X-rays due to friction, heating matter to millions of degrees. This radiation would cook you long before tidal forces became lethal. You'd be bathed in high-energy X-rays and gamma rays, receiving fatal radiation doses in seconds. Stellar mass black holes formed from collapsing stars likely rotate rapidly. The collapsing core spins up due to conservation of angular momentum. This creates a Kerr black hole with ergosphere, frame dragging, and potentially ring singularity. But the mass inflation and instabilities probably destroy the exotic inner structure, replacing it with chaos. Intermediate mass black holes, perhaps 100 to 100,000 solar masses, might exist in globular clusters or as building blocks of supermassive black holes. Their event horizons are larger, from hundreds to thousands of kilometers. Tidal forces at the horizon are moderate. You might survive to the horizon or close to it before being torn apart. The journey from horizon to singularity takes seconds to minutes. The experience is still violent, but somewhat less instant than with stellar mass black holes. Supermassive black holes, lurking in galaxy centers, have masses from millions to billions of solar masses. Their event horizons span millions to billions of kilometers, comparable to our solar system's scale. Tidal forces at the horizon are gentle. You cross the horizon intact, alive, aware. The journey from horizon to singularity takes minutes to hours. You have time to experience the interior, to observe the strange effects, to contemplate your fate before tidal forces grow lethal as you approach the singularity. This difference is profound. With stellar mass black holes, you never experience the interior as a conscious observer. You're dead before crossing. With supermassive black holes, you might spend minutes or hours inside, conscious and aware, experiencing the ultimate unknown. What about primordial black holes, hypothetical tiny black holes formed in the early universe? If one had a mass of a mountain, 10 to the 15th grams, its event horizon would be about 10 to the minus 13 meters, smaller than an atomic nucleus. The tidal forces at the horizon would be incomprehensibly large. Approaching within meters of such a black hole would tear you apart at the molecular level. Approaching within millimeters would disrupt atoms. Crossing the horizon, you'd be torn apart at scales smaller than particles. The singularity would be reached essentially instantaneously, far less than any measurable time. The entire journey from horizon to singularity might be less than 10 to the minus 40 seconds. You'd be destroyed so quickly that no signal could propagate across your body during the destruction. Conversely, what about maximally large black holes? The observable universe has an edge about 46 billion light-years away. If a black hole had the mass of the entire observable universe, about 10 to the 53 kilograms, its event horizon would be comparable to the observable universe's size. Tidal forces at such a horizon would be unimaginably weak. You could cross the horizon and not notice for billions of years. The journey from horizon to singularity would take trillions of years. Of course, such a black hole doesn't exist. Our universe is not inside a black hole of this size, as far as we know. But the hypothetical illustrates the scaling. Larger black holes give gentler tidal forces and longer times. What about charged black holes, Reissner-Nordström black holes? Electric charge creates repulsion that opposes gravitational attraction. A highly charged black hole would have bizarre properties. It might have an inner and outer horizon, like a Kerr black hole, but due to charge rather than rotation. As you approach, the electric field would be intense. If you carry any charge, as all normal matter does, you'd experience enormous electric forces. These might tear apart molecules, ionize atoms, create violent electromagnetic effects. The approach could be energetically catastrophic even before gravitational effects dominate. Inside a charged black hole, the structure is mathematically similar to a Kerr black hole, with similar exotic features and similar instabilities. The inner horizon likely suffers mass inflation, destroying the smooth structure. In practice, charged black holes probably don't exist in nature. Any significant charge would attract opposite charges from the surrounding plasma, neutralizing the black hole quickly. Astrophysical black holes are expected to have negligible net charge. What about black holes in higher dimensions? String theory suggests the universe might have extra spatial dimensions beyond the familiar three. In such scenarios, black holes could have different geometries and properties. In higher dimensions, event horizons might not be spherical. They could be black brains, higher dimensional surfaces. Falling into a black brain might involve different physics, different tidal effects, different horizons. This is highly speculative, but if extra dimensions exist and black holes reflect this, the experience of falling in could differ fundamentally from what we've described. What about extremal black holes at the theoretical limit of rotation or charge? A maximally rotating Kerr black hole has its inner and outer horizons coinciding. The structure becomes degenerate. Approaching such a black hole, you'd encounter infinite time dilation at the horizon. You'd never reach it in finite time, even in your own reference frame. Extremal black holes are probably unstable and don't exist in nature. Any perturbation like matter falling in would push them away from extremality. But they're mathematically interesting and might reveal features of quantum gravity. The key point is that falling into a black hole is not a single experience, but a spectrum depending on mass, rotation, charge, and other factors. The common thread is the event horizon, a point of no return, and the singularity, a region where physics breaks down. But the details vary enormously. For a human, the most likely scenario to permit conscious experience inside would be falling into a supermassive black hole with minimal accretion and rotation. You'd approach, cross the horizon intact, spend minutes to hours inside experiencing bizarre, relativistic, and quantum effects, and finally be destroyed as you approach the singularity. Let's piece together what those final moments might actually be like, combining everything we've learned. You're falling toward a supermassive black hole, say 10 million solar masses, with an event horizon radius of about 30 million kilometers. You've crossed the horizon and have been falling for 20 minutes by your clock. You have perhaps 10 minutes left before reaching the singularity. You look outward, toward where you came from. The universe outside is still visible, light from it reaching you across the event horizon. But time dilation effects are extreme. Events outside that took years now appear compressed into moments. You might see stars evolving, orbits changing, the slow evolution of the cosmos accelerating. The view is also distorted by aberration and Doppler effects. The light is intensely blue shifted. What was visible light is now ultraviolet or X-rays. The cosmic microwave background, normally invisible, has been blue shifted into visible light, creating a glow across the sky. Stars ahead of you, in the direction you're falling, appear crowded and compressed by aberration. Stars behind appear spread out. The view is not what you'd see from outside, it's a relativistic hall of mirrors. Looking inward, toward the singularity, you see darkness. Nothing comes from ahead, only you, and everything else that's fallen in is here. You might see light from other infalling matter, if any. A doomed astronaut who fell in before you might be visible ahead, a ghost image compressed and distorted. You feel tidal forces growing stronger minute by minute. Initially gentle, they're now uncomfortable. Your body aches. Your spine feels stretched. Blood pressure is changing. You have a persistent sensation of being pulled apart. Your instruments, if you have them, show bizarre readings. Clocks compared to distant references show extreme time dilation. Gravimeters show increasing tidal gradients. If you drop an object, it falls away from you faster than normal tidal effects make things spread apart. The darkness ahead might not be completely dark. Quantum effects near the singularity could produce radiation, though we don't know. You might see strange flashes or glows, quantum fluctuations made visible by extreme conditions. As minutes pass, tidal forces intensify. With 5 minutes left, you're in pain. With 2 minutes left, you're in agony. Your body is visibly stretching. Your height has increased noticeably. Skin is taut, joints stressed, bones bending. With 1 minute left, you're being torn apart. If you're still conscious, which is doubtful, you experience the worst pain imaginable. Your body's structural integrity is failing. Tissues are tearing. Blood vessels are rupturing. In the final seconds, whatever remains of consciousness fades. Your body is no longer recognizably human, stretched into a long, thin thread. Molecules are being pulled apart. Atoms are being ionized. The visual environment might become chaotic. If quantum effects are strong near the singularity, you might see particle creation, pairs of particles materializing from vacuum, glowing and annihilating. Spacetime itself might appear to boil at the Planck scale, and then you reach the singularity. What happens at that exact moment? Classical general relativity says tidal forces become infinite. You're compressed to infinite density in some directions, stretched infinitely in others. Space-time curvature diverges. But quantum gravity, whatever it is, likely replaces this with something else. Perhaps you're crushed to Planck density, and then transformed. Into what? Quantum string states? Discrete quantum geometry? A different phase of matter or space-time? Or perhaps you bounce, emerging into another region of space-time through a white hole. Or perhaps your information is encoded into the black hole's quantum state, preserved but scrambled beyond recognition. We don't know. The moment of reaching the singularity is where physics becomes speculation. We can describe the approach with some confidence using general relativity, but the singularity itself requires new physics we don't have. From your perspective, it's the end. Your conscious experience ceases. Your body, if any remnant remains, is destroyed absolutely. The atoms that were you might persist in some form, but not in any arrangement that resembles you. From the distant observer's perspective, you never reached this point. You're still frozen at the event horizon, fading into invisibility, existing eternally in their reference frame at the moment just before crossing. Both descriptions are true in their respective frames. You experience the journey, the crossing, the destruction. The observer never sees you cross. These facts coexist without contradiction in general relativity's frame-dependent reality. If you could somehow send a message describing your final moments, it would never arrive. Any signal you emit inside the event horizon falls toward the singularity with you. The observer outside receives nothing. Your fate is forever hidden behind the horizon. This is the ultimate isolation. Once inside, you're cut off from the universe absolutely. No information, no signal, no particle can escape to tell your story. The event horizon is a one-way membrane through which information flows in but never out. And yet, paradoxically, the observer outside sees you at the horizon forever. Your image, frozen and fading, remains eternally. In a sense, you're everywhere inside experiencing the end, outside frozen at the boundary, and in the Hawking radiation, eventually encoding your information. The black hole consumes you, but in doing so, creates one of the deepest puzzles in physics. Your fate is uncertain, your information's destiny unclear, your final moment a mystery that touches the foundations of reality. We've journeyed to the ultimate extreme, falling into a black hole, crossing the event horizon, descending to the singularity. We've explored the strange effects, time dilation, spaghettification, the observer paradox, quantum mysteries. What have we learned? That black holes represent the edge of our knowledge. General relativity describes them beautifully but breaks down at the singularity. Quantum mechanics demands information preservation but struggles to reconcile with black hole evaporation. The experience of falling in depends crucially on the black hole's mass. For stellar mass black holes, you die before crossing, torn apart by tidal forces in a fraction of a second. For supermassive black holes, you might survive crossing the horizon, experiencing minutes or hours inside before final destruction. From your perspective, the journey is finite and definite. You cross the horizon, fall to the singularity, experience the end. From distant observers, you appear frozen at the horizon forever, never crossing, never ending. Both perspectives are valid, both are real, both are true. Black holes embody the deepest mysteries of physics. What happens at the singularity? Is information destroyed or preserved? Does quantum gravity resolve infinities or create new phenomena? Are there white holes, wormholes, other universes? We don't have answers, but we're making progress. Hawking radiation, holography, string theory, loop quantum gravity, all are providing insights. The information paradox, once seeming intractable, now has multiple promising approaches. Future theories will likely reveal that black hole interiors are even stranger than we imagine. The singularity might not exist as classical theory predicts. The interior might be connected to other regions in ways we don't understand. Information might escape through mechanisms we haven't discovered. But for now, black holes remain the ultimate mystery. They're real, we've observed them through gravitational waves, through X-ray emissions, through the Event Horizon Telescope image of M87's black hole. They exist in nature, not just in theory. And yet we cannot see inside. The Event Horizon cloaks the interior absolutely. We can theorize, calculate, speculate, but we cannot observe. The interior is forever hidden. If you fell into a black hole, you'd experience something no one outside would ever see. You'd cross the ultimate boundary, enter the ultimate unknown, and reach a fate that physics cannot yet describe. It would be the most extreme experience possible, a journey to where space-time itself breaks down, where the laws of physics fail, where reality becomes something beyond our current understanding. As you drift towards sleep, imagine that journey one more time. Imagine approaching the black hole, feeling gravity intensify, seeing the universe distort around you. Imagine crossing the horizon, the point of no return, stepping beyond all possibility of return. Imagine the final descent toward the singularity, time dilating, tidal forces growing, the universe accelerating its evolution outside as you fall deeper inside. Imagine the final moments as physics breaks down, as space-time becomes something unknown, as you reach the end of describable reality. Black holes are real. They're out there, lurking in galaxy centers, scattered through space, waiting. They represent not just astrophysical objects but fundamental puzzles about the nature of reality. What happens if you fall into a black hole? The honest answer is, we don't fully know. We know parts of the story. We know the approach, the horizon crossing, the mathematical singularity, but the complete story requires physics we haven't discovered. That's the beauty and the terror of black holes. They're mysteries at the heart of reality, places where our knowledge ends and the unknown begins. They're the ultimate frontier, the final edge, the deepest question. Rest well, knowing that the universe contains these wonders. Tomorrow, you'll wake to a world of familiar physics, predictable forces, understandable nature. But out there, black holes wait portals to the extreme, gateways to the unknown, monuments to the limits of human knowledge. Sweet dreams of falling through space-time, of crossing event horizons, of reaching toward singularities where physics and reality merge into mystery. The black hole's interior remains unknown, but that unknown inspires us to keep questioning, keep exploring, keep pushing toward understanding. And perhaps someday, we'll know what really happens when you fall into a black hole. Until then, it remains the ultimate journey, a trip to the edge of knowledge itself.